multiple capacitors in parallel may be replaced by a single capacitor called an equivalent capacitor. Suppose we have two capacitors in parallel. These two capacitors in parallel are attached to the same 2 points, A and B. The first capacitor we'll call C1 and the second capacitor we'll call C2. These two capacitors can be replaced by a single equivalent capacitor. This equivalent capacitor will have a capacitance equal to some combination of the first two capacitances of the capacitors. C12 is our equivalent capacitance. Because capacitors in parallel share the same 2 points in common, all capacitors in parallel with each other have the same potential difference between their plates. Now, this is because electric potential difference is path independent. And what that means is if we measure the potential difference across capacitor 1, we would get the potential difference being equal to the difference in potential between the points A and B. If we then measure the potential difference across capacitor C2, we would measure that the potential difference across capacitor C2 is also equal to the difference in potential between points A and B. Because of path independence, this means that the potential difference across capacitor 1 is equal to the potential difference across capacitor 2. And you know what? Since those two capacitors can be replaced by a single equivalent capacitor, we could say that the equivalent capacitance is equal to, or we could say the potential difference of the equivalent capacitor is equal to the potential difference of each of the capacitors in parallel. And this is true for any number of capacitors in parallel, and not just capacitors, any component, whether it's capacitors, resistors, or lights. Components in parallel have the same potential difference between their ends due to path independence. Another property of capacitors in parallel is that the charge of the equivalent capacitor is equal to the total charge of each of the capacitors in parallel. So if we take a look at our two capacitor systems, each of these capacitors have a certain amount of capacitance, and each one has the same potential difference. So let's take a look at that. If we look at capacitor 1, it's going to accumulate a total amount of charge Q1. And we can determine how much charge it accumulates from Valley College's quaint, which tells us that the amount of charge on capacitor 1 is equal to the product of the capacitance of capacitor 1 times the potential difference across capacitor 1. This is just equal to the product of the capacitance of capacitor 1 times the potential difference from A to B for this example. Now for capacitor 2 will have an amount of charge equal to the product of its capacitance times the potential difference from A to B. So what this means is if the capacitances are different, then the charges on each of the capacitors will be different. So the charge on capacitor 2 is equal to Q2. Now the total charge is equal to the sum of Q1 and Q2, the charge on each of the capacitors. And that total charge also is equivalent to the charge of our equivalent capacitor. In other words, the charge of the equivalent capacitor is equal to the sum of the charges of each capacitor in parallel. We can use this to show that the equivalent capacitance of capacitors in parallel is equal to the sum of the capacitances of the individual capacitors. To show this, let's take an arbitrary combination of capacitors in parallel. So this can go up to any number of capacitors wired in parallel between the same 2 points. Now, let's use the fact that we know that we could replace this combination of parallel capacitors with a single equivalent capacitor. And we know that the charge on this equivalent capacitor is equal to the sum of the charges on each of the individual capacitors. Well, using Valley College is quaint. We know that the potential difference across the equivalent capacitor times the equivalent capacitance is equal to the charge on the equivalent capacitor. And in fact, the product of potential difference and the capacitance for capacitor 1 is equal to the charge on capacitor 1. And the product of the potential difference from A to B and the capacitance for capacitor 2 is equal to the charge on capacitor 2. And we could do this for any number of capacitors in parallel in our circuit. So notice what's common to each term: the potential difference from A to B. Since the potential difference from A to B is common to each term, we can divide it out, leaving us with an expression for the equivalent capacitance of an equivalent capacitor is equal to the sum of the capacitances for each capacitor in parallel. So in other words, if you have 2 or more capacitors in parallel, the equivalent capacitance is the sum of them. This is different than what we learned when we looked at capacitors in series. For capacitors in series, we saw that the equivalent capacitance is equal to the reciprocal of the sum of the reciprocals of each of the capacitances in our combination. So if you want to lower the equivalent capacitance of a circuit, wire them in series. If you want to increase the equivalent capacitance of a circuit, wire them in parallel.